chemistry, we're moving on to a new topic of VSEPR, VSEPR. So VSEPR, often said VSEPR, stands for valence shell electron pair repulsion. VSEPR provides a set of rules by which the three-dimensional geometry of a molecule can be determined by its Lewis dot structure. According to the VSEPR model, bonding domains space themselves at equal angles, and non-bonding domains, lone pairs, repel bonding pair electrons to change the bond angle. So we're going to see what all of that means. So an electron domain is anywhere a pair of electrons exists. An electron domain can be either a lone pair, a single bond, a double bond, or a triple bond. Any of those is one electron domain. A bonding domain is an electron domain that bonds two atoms. A bonding domain can be a single bond, double bond, or triple bond, anything but a lone pair. So any one of those is one bonding domain. A bond angle is the angle that two terminal atoms, those are the ones on the outside, that would be the white spheres there, make with the central atom. So there's the central atom, there are the two terminal atoms, and there's the bond angle. So we're going to be discussing bond angles as we discuss the geometry of the molecules. So let's take some examples to learn the difference, learn what a bonding domain and an electron domain is. So an electron domain is anywhere a pair of electrons exists, whether they're bonding or not. A bonding domain is an electron domain that bonds two atoms. So there we see the double bond between carbon and oxygen. That is an electron domain, one electron domain. It's also one bonding domain. Similarly, that double bond is one electron domain and one bonding domain. That lone pair is an electron domain, and it's a non-bonding domain. That's an electron domain and non-bonding domain. Electron domain and non-bonding domain. And same thing there, electron domain and non-bonding domain. Let's go over to the other molecule. That's an electron domain and a non-bonding domain. This triple bond is one electron domain and one bonding domain. The word domain just means a place, a location. And finally, this single bond is one electron domain and one bonding domain. The formula for molecular geometry has three parts. The letter capital A represents the central atom in a molecule. The X represents the number of bonding domains, so that number will be the N down there. So it'll be X with a subscript of N. That's how many bonding domains. And the E represents the non-bonding domains. It also has a subscript to tell you how many. Sometimes I refer to this as AX notation, AXE, AX notation. So here's an example, AX2E1. This is a molecule with a central atom A and three electron domains. Two are bonding domains and one is a non-bonding domain. Okay, so let's start looking at, we're going to start with the simplest. This is an AX2E0. That means it has two bonding domains. So you have a central atom, that's the pink sphere, and two terminal atoms, those are the white spheres on the outside. That pink and white tube represents a bonding domain. It could either be a single bond on each side, a double bond, or a triple bond, but it's a bonding domain. So it's saying you have two bonding domains, that's the X2, and no lone pairs. So that has a domain geometry of linear. It's going to create a straight line molecule such as carbon dioxide. It also has a molecular geometry of linear because there are no lone pair. So you'll see some contrast to that in the next few examples. So a linear domain geometry means that the molecule has two electron domains, The molecular geometry is also linear since both are bonding domains. The molecule is a straight line and has a 180-degree angle. And the example there is CO2. Note, when there are only bonding domains, in other words, E is 0, there's no lone pairs, only bonding domains in the molecule, the domain geometry and molecular geometry will be the same. So linear in this case. So this is called a trigonal planar domain geometry, and that means that the molecule has 3 electron domains. All 3 are bonding domains, as you can see, X3. The molecular geometry is also trigonal planar because all 3 are bonding domains. The molecule is flat and has 3 120-degree angles. So the molecule wants to make its bond angles equal. It wants to spread those electrons out as evenly as possible. The name means that it has the shape of a triangle, as you can see, and it's entirely flat. It's on the same plane. Now, when there are only bonding domains, as there are here, no lone pairs, in a molecule, the domain geometry and the molecular geometry will be the same. So trigonal planar, trigonal planar. Okay, now what we're going to do is we still have 3 electron domains. AX2E1, that's a total of 3 electron domains. This time 2 of them are bonding and 1 of them is non-bonding. That's the lone pair you see on the image there. So that's still a domain geometry of trigonal planar because it has 3 electron domains. But an AX2E1 is going to produce what's called a bent molecule. So a trigonal planar domain geometry means that the molecule has 3 electron domains. There are 2 bonding domains and 1 non-bonding domain. This results in a bent molecule. A bent molecule forms when 2 atoms form an angle with the central atom. The non-bonding lone pair electrons repel the bonding electrons. This pushes the angle from 120 degrees, as you saw in the last slide, down to 119. So the lone pair on the top are pushing that pink and white tube again is the bonding electrons between, in this case, it's sulfur dioxide. It's between the sulfur and each of the oxygens. So that lone pair is pushing down on it. It's going to squeeze that bond angle down from 120 to 119. Now we move up to AX4E0. So this is a tetrahedral domain geometry. A tetrahedral domain geometry means that the molecule has 4 electron domains. There are also 4 bonding domains here. This results in a tetrahedral molecular geometry. When you have a tetrahedral molecular geometry, all 4 bond angles are 109. So this is what a methane molecule looks like. So it's not the flat CH4 that we draw on the board. It actually has a 3-dimensional structure to it. So all of those bond angles want to be equal. They want to spread out, the electrons want to spread out evenly. So this is called a tetrahedral molecule. Now we're going to take one of those hydrogens off the tetrahedral molecule. It's still a tetrahedral domain geometry because it has 4 electron domains. X3 plus E1, 3 plus 1 is 4. That means 3 of them are bonding. 1 of them is the lone pair that you see on the image there. So that creates a molecular geometry of trigonal pyramidal. So a tetrahedral domain geometry means that the molecule has 4 electron domains. 3 of the domains are bonding domains, and 1 is the non-bonding lone pair domain. This results in a 3-faced pyramid-shaped molecule. It's hard to tell it in this image. It looks flat, but it's actually a pyramid. The pink, the central nitrogen there, is higher than those 3 hydrogens. They're down lower. So it's forming a 3-faced pyramid. And so that's called a trigonal because it's in the shape of a triangle, pyramidal because it's actually a pyramid. It's not a flat molecule. Flat is planar. This is pyramidal, like a pyramid. The three bond angles are less than 109 degrees because the non-bonding pair, that lone pair up on the top, pushes down on the three bonding domains. So you can see in blue it says the non-bonding lone pair pushes down on the bond angles. So that makes the bond angle a little bit less than 109. Now we're still in the tetrahedral domain geometry family. That means we have 4 electron domains. This is AX2E2. So 2 of them are bonding, 2 of them are lone pairs, as you can see in the diagram. And that creates a bent molecular geometry. Now this is the second time we've seen a molecular geometry of bent. This one is different than the one you get with the trigonal planar. It's going to have a different bond angle. So this is an example of a water molecule, H2O. So water is a tetrahedral type domain geometry, and it is bent. Its molecular geometry is bent. So a tetrahedral domain geometry means that the molecule has 4 electron domains. When 2 of the domains are bonding and 2 are non-bonding domains, it results in a bent molecule. This bent molecule has a different bond angle than the trigonal planar bent molecule we saw a few slides back. This is the geometry of a water molecule and produces a 104.5 degree bond angle. So that's 4.5 degrees less than the full 109 degree tetrahedral bond angle that CH4 had. So now you see why a water molecule is bent and not linear. Those 2 lone pairs are not on opposite sides of that oxygen, that central oxygen. If they were, water would be linear. But they're not. It's actually a tetrahedral shape in which you've pulled off 2 of the hydrogens, and now the central atom is oxygen, and so now it forms a bent molecule. Now, we're going to introduce a concept here called the extended octet. So an extended octet means that an element in the 3rd row and below can store up to 2 additional pairs of electrons, that's 4 total electrons, in its empty d orbital. So up until now, our bonds with the central atom could only have a total of 8 electrons, 2 in the s subshell and 6 more in the p subshell, so that would be a total of 8. So CH4 is an example. Carbon can bond and have 8 valence electrons around it. Okay, you've seen CH4 before. But now we're getting into some elements that can actually have more than 8. They can have either 10 or 12. So let's look at a couple of those. So this molecule right here has an AX5E0 geometry. You can see that it's bonding in 5 different directions, and each of those has one single bond. So that's a total of 10 electrons. So there are 5 bonding domains, each with 2 electrons for a total of 10 electrons. 2 of the electrons, that's one of the pairs, is held in the d subshell. So anything from the 3rd row down is going to have a d subshell. So if you look at your periodic table, have that out in front of you. If you look at aluminum, silicon, phosphorus, sulfur, chlorine, not argon, those have an empty d subshell. And so they can use it kind of like a storage locker. They can store 2 additional electrons, 1 pair, down in their d subshell. So this is called an extended octet. It actually has 10 bonding electrons, not just 8. And you can also have another pair. So this molecule has an AX6E0 geometry. It bonds in 6 different directions. There are 6 bonding domains, each with 2 electrons for a total of 12 electrons. So 2 pairs of electrons are held in the d subshell. You can't go beyond 6. Okay, there's nothing beyond 6. And even this theory is a little bit controversial, but this is generally what's accepted as to what's happening in some of the bonds. So now you're going to see some examples of these types of bonds, extended octets. Okay, so this is trigonal bipyramidal. So look at that shape right there. It has a 3-sided pyramid on the top. If you were to put faces in between those terminal those terminal atoms, those white spheres, you would have 3 faces on the top, and then you'd have 3 faces on the bottom. You'd have an upside down pyramid, an inverted pyramid. So it's trigonal because each of the pyramids has 3 faces. That's triangle. And bi means there's 2 pyramids. There's one on the top and there's one turned upside down on the bottom, and they are pyramids. So that's trigonal bipyramidal. So that's an AX5E0. This is an example of an extended octet with 2 more electrons than the usual octet of 8 that we're used to seeing. So there's no lone pair, so the molecular geometry is also trigonal bipyramidal. A trigonal bipyramidal domain geometry means that the molecule has 5 electron domains. All 5 domains are bonding domains. Now, there's names for each of these. The 3 that are around the center that go around on the sides are called equatorial, like the equator of the Earth. They're equatorial. And the one on the top and the one on the bottom are called axial. That's like the North Pole and the South Pole, in a sense. So this results in 2 3-sided pyramids. One is an upright trigonal pyramidal, and the other is an inverted or upside down trigonal pyramidal. The bond angle between the equatorial atoms, the 3 with E's, is 120 degrees. And the bond angle between the axial, the ones on the top, and the equatorial is 90 degrees, or the one on the bottom also. Okay? All right, so that's an extended octet. Now we're going to go and continue with the 5 electron domains, but we're going to take away one of those atoms. So kind of get this image in your mind when you look at the next slide. Okay, now we're also trigonal bipyramidal domains. X4 is 4 bonding, E1 is 1 non-bonding, so that's a total of 5. So we still have 5 electron domains. That's still the trigonal bipyramidal family. But now what they've done is, you got to kind of picture that last slide. They took the axial and they turned them on their sides. So those 2 that are on the right and the left are the axial. They turned this on the side. And what they did was they pulled away one of the equatorial. So now you have 2 of the equatorial, those are the ones down on the bottom, and one of them that was pulled away, that's the lone pair on the top. And then the 2 axial are on the right and the left. So you see this kind of looks like a teeter-totter or a seesaw, what some people would call a seesaw, what little children go up and down on. So they call this the seesaw structure. Okay. So a trigonal bipyramidal domain geometry means that the molecule has 5 electron domains. In this case, 4 of the domains are bonding domains and 1 is non-bonding. This is called a seesaw. The molecule is turned on its side to look like a seesaw. All 4 bonds are pushed downward, so the 2 equatorial atoms are less than 120 degrees. And the 2 axial atoms, the ones on each side, are less than 180. They're kind of squeezed down. So that's what lone pairs do. They change the bond angle from what it would be if there were no lone pairs. They're pushing on the bonding electrons, that's the pink and white tubes, and they're pushing all of them downward to squeeze the bond angle together. So this example is sulfur tetrafluoride. The non-bonding electrons push the axial atoms down, producing a bond angle less than 180 degrees. That's the A and the A. The equatorial atoms are pushed together to an angle less than 120 degrees. That's the E and the E. Okay, now we're going to take away 2 of the equatorial atoms. This is the same family, domain geometry, trigonal bipyramidal. And now we've taken away 2 of the equatorial atoms, so now the only one left is the one that's pointing down. That's the equatorial. The axial are still the ones on the side. So this is an AX3 because there's 3 bonding domains, E2 because there's 2 lone pairs there. And this is called a T-shape. That makes sense. So a trigonal bipyramidal domain geometry means that the molecule has 5 electron domains. If 3 of the domains are bonding domains and 2 are non-bonding, this produces a T-shape. 2 of the equatorial atoms have been removed. The 2 non-bonding electron pairs push both of the bond angles down to form angles less than 90 degrees. So this is chlorine trifluoride. The non-bonding electrons push the axial atoms down, producing a bond angle of less than 180 degrees. It turns the axial are getting pushed down, and then in between the axial and the equatorial, it's less than 90 degrees. Now we're getting into our final family, our final domain geometry, that's octahedral. So look at that shape. It looks like a pyramid, like an Egyptian pyramid, a four-sided Egyptian pyramid on the top. And then on the bottom, there's an inverted, upside down, four-sided Egyptian pyramid. So that's if you put faces in between all of those outside those white spheres. So that's called octahedral. There's 4 faces on the top and 4 faces on the bottom. That's 8, octahedral. So this is an AX6E0. So this is the molecular geometry is octahedral. An octahedral domain geometry means that the molecule has 6 electron domains. When all 6 are bonding domains, the molecular geometry is also octahedral. All of the bond angles you see here are 90 degrees between each of those. So this is sulfur hexafluoride, and all bond angles are 90 degrees. Okay, now we're still in the octahedral domain geometry, but we've taken away one of the atoms, the one at the bottom. So this is an AX5E1. So it still has 6 electron domains, so it's still octahedral. But it now forms a new shape called the square pyramidal. It looks like an Egyptian pyramid. If you put faces between those white spheres, those terminal atoms, it would be a 4-faced pyramid, and that's the way the Egyptian pyramids look. So an octahedral domain geometry means that the molecule has 6 electron domains. When 5 are bonding and 1 is non-bonding, the molecular geometry is square pyramidal. The non-bonding electron pair pushes the 4 equatorial bonding electrons E upward toward the axial atom. So you can see how that lone pairs always push on bonding pairs of electrons. In this case, it's pushing them from the bottom upward. So now they're kind of squeezed upward a little bit. So this is bromine pentafluoride. The equatorial bond angles are still 90 degrees, slightly less actually. The bond angles between the equatorial bonds and the axial bond is less than 90 degrees. So everything's getting pushed upward except the A atom is not. Okay, now we've taken off 2 of the atoms. Still octahedral domain geometry, AX4E2, so now you have 2 lone pair. Now it was hard for me to do this image properly. Those 2 lone pairs are an exact opposite side of that central pink atom. So that pair on the bottom should be directly underneath the pink atom. So this is called square planar because it's square and it is flat. It's flat on a plane. Why? Because those 2 lone pairs, if they're exactly opposite each other, they're pushing up and down equally, so it's going to maintain a square shape. They're not the terminal atoms, those 4 white spheres are not going to either be pushed up or down. So an octahedral domain geometry means that the molecule has 6 electron domains. When 4 are bonding domains and 2 are non-bonding domains, the molecular geometry is square planar. All 4 bonding domains are on a flat plane. The non-bonding electrons pairs push the bonding domains equally on top and bottom. For this reason, the molecule is flat. So this is xenon tetrafluoride. You notice that this is a noble gas that can bond. Xenon, one of the bigger noble gases, can bond. So it has equatorial bond angles between those 4 white spheres of 90 degrees. The non-bonding electrons on top and bottom provide equal and opposite force to the bonding domains, so they don't push in either direction. All right, that takes care of our lesson on valence shell electron pair repulsion, and we'll practice some of these on the assignment.